This might be our last video on torque and rotational motion, and in this video more like practice, so you're gonna see different type of questions: rotational, angular, torque. So in this video I'm gonna start with this problem, which is very interesting, and so go ahead, pause, read the question, and then write everything that is given, and then let's talk about how to solve this question. So the information that is given: the mass of the solid cylinder is given, the radius of the solid cylinder is given 10 centimeters, which is 0.1 meter. The length it rolls down, which is 6 meters, and the height at which the how tall the house is, which is 5 meters, and the angle at which the roof meets the horizontal line with the house on the top. And so we need to find the angular speed of the cylinder before about its center as it leaves the house roof. So I'm going to use the conservation of energy to solve this question. And let me choose the black color here. So if this is the height h, then the potential energy, gravitational, and I'm going to say the bottom of the roof is potential energy is equal to 0. So the potential energy of the cylinder, gravitational potential energy, will go into two types of energy at the end of the roof. One of them is going to be the kinetic energy, rotational. So I'm going to do like rotational. And the other one is going to be just the kinetic energy because it's rotating and moving forward. So I can say that mgh is equal to 1/2, and its inertia, omega squared at the end, the final velocity, because initial is 0, and plus 1/2 mv squared. And also inertia, because it is a disk, so the inertia of the disk, if you remember, is equal to 1/2 mr squared. So I'm going to plug this into my equation. So I have mg, and h from this right triangle right there on the top of the roof, h is equal to 6 sine theta. So if I call my L is 6, so this is my L, then I'm going to write L sine theta equals to, and then I have 1/2, and then inertia is also again 1/2, and then mr squared times omega squared plus 1/2 mv squared. And the velocity that this v is, the velocity is the one that it will have by the time it reaches the bottom. Then I'm going to times them all by 4 to get rid of the fraction, because I have 1/4 right here. And I also have to remember this formula. Let me maybe choose different color. That linear velocity during the rotation is equal to r times omega. So if I have squared, r squared, then it's r squared omega squared. And here I have r squared omega squared. So I can replace this one with just the v squared. So now I'm going to have times by 4. 4 mg L sine theta equals to times this by 4. 1/4 goes away, and I have m. And instead of r squared omega squared, I have v squared. And then times the next term by 4 gives me 2 mv squared. So I actually have 3 mv squared if I collect like terms. So both sides have the mass, so I'm going to cancel the mass from both sides. And the velocity on the end is equal to the square root of 4gl sine theta divided by 3. And if I plug in my numbers, then I'm going to get 6.32 meters per second. And if I wanted to know angular velocity at the end, then I would divide both sides by r from the formula that I wrote on the above in blue. So if I divide both sides by r, so that will give me 63.25. So this is 63.25 radians per second. So I could also have angular velocity at the end of the length of the roof. So I found angular velocity, which is 63.25 radians per second, and linear velocity, the one that you see on the graph, is 6.32 meters per second. So I have this linear velocity. I'm going to erase some works a bit so I have more space to solve the rest of the question. So here I have this velocity that I just found. This is the velocity of 6.32. And it has a vertical component, Vy, so I'm going to call it the Vy. And it has horizontal component, which is Vx. And the angle there is 30 degrees. So Vx is, maybe I'm going to write it here, Vx is equal to V cosine theta. And theta is 30 degrees given in the problem. So right there you can see this is 30 degrees in the diagram. And then Vy is equal to V sine theta. So I can calculate what this equals to. So I got Vx is 547 and Vy is 316 meters per second. I didn't write meters per second, doesn't fit there. So I'm just gonna leave it this way. And then I can find the final vertical velocity. So I'm gonna switch to purple. So by the time the object or the cylinder reaches the bottom, it will have vertical velocity Vy. So I'm gonna call this purple arrow that you see right there in my diagram is my vertical velocity V final, and I have the distance and I have acceleration due to gravity, so I can use the Dow formula, the one that I taught you about in kinematics. So we have initial velocity is square root of 2, acceleration, the distance it's fallen is 5 meters, and plus initial velocity, vertical velocity initial, because we don't look at the horizontal motion right now, we're just looking at the vertical velocity. So the vertical initial velocity is Vy, and that one is 316 squared. So I can find that the final velocity is going to be equal to 10.49 meters per second. And since I know this final velocity, I can find the time it will to fall on the ground. It takes to fall on the ground. So that's going to be change of the vertical velocity over the acceleration. If I use acceleration formula, so the final velocity vertical is 1049, and the initial vertical velocity is 316, and the acceleration is 10. So from here, I can find that the time it will take to fall on the ground from the edge of the roof is 0.732 seconds. And now I'm gonna look at the horizontal distance. So now I can find this horizontal distance from the diagram. So I'm looking for this distance d. So that horizontal distance d is equal to Vx times the time. And I found what Vx is equal to, that's 547. And the time is 0.732. And that gives me that the cylinder will land 4.03 meters away from the edge of the roof. It reminds us the question that we did, the Santa question, but in this case you also have to calculate potential energy goes into kinetic energy plus the kinetic rotational energy. So if something is rotating, it rotates and it has energy, it takes that energy from the potential energy. So very good example. I haven't seen this on AP exam, but you probably will see this at the university. Here's another very interesting question. I have seen it somewhere in the multiple choice on AP exam, so it's worth to learn this question. And go ahead, pause, read the question, and then try to solve the question. Let's see how much you can get without my help before I help you. And maybe some of you will be able to solve it without me. So the question is given that there are masses m, and 2m, and they want you to find what is the value of the lowercase m in terms of the capital M's, and in order for this system to stay in equilibrium. And I can use the torque. So I'm gonna make the point of rotation the center of the circle, and I have mg is positive. The mg is positive. The distance is r actin, and the angle between the force and the horizontal is 90 degrees. So sine of 90 degrees is 1. Then I have the other one is negative 2m acting on it, g, and the distance is also r, and sine of 90 degrees is also 1, and it's negative because it would make the wheel or rotate in the clockwise direction, and the lowercase m would make the wheel rotate in the counterclockwise direction. And for the mass m, this is the tricky part. So I'm gonna say it would make the object rotate in the positive direction, counterclockwise. So I'm gonna say plus mg, but then the distance is in green because that's how far the force is acting away from the distance from the point of rotation, which is r cosine theta. And so that's the distance, but the angle with the mass and the horizontal line is still 90 degrees, so sine 90 will give you a 1. And that is equal to 0 because it is in equilibrium. So what I did is the sum of all the torques is equal to 0. And now I'm solving for little m. Oh, all of them have r and all of them have g. So I can cancel all the g and r's from all of them, or divide all of them by rg. And now I'm going to solve them all for m. So the m is equal to, it is 2m minus m cosine theta. Or it's the same as m 2 minus cosine theta. So m is equal to 1.5, the mass that they ask you in terms of that mass to find what little m is equal to. So here's another question that I want to look with you at. A rod of length m, l, and a negligible mass is pivoted at the point that is off center with the length shown in the figure on your right. The figures show two cases in which masses are suspended from the end of the rod. In each case, the unknown mass m is balanced by the known masses, so m1 and m2. So m1 or m2, so that the rod remains horizontal. What is the value of m in terms of unknown masses? In terms of the known masses, m1 and m2. So I'm going to use the concept of rotational equilibrium. So the sum of the torques in the first question, or in the first picture, and the second one is going to be equal to 0. So for each one, I'm going to use this concept. So for the first one, I have m, and it would make the bar or the level rotate in the counterclockwise direction. If the other m1 wasn't in the picture, then it's positive. So mg, the force acting, and the distance from the point of rotation is L1. And then for the second mass, that one would make it rotate in the negative direction, so it's negative m1g. And the distance is L2. And the angles are sine 90 degrees, so that is just 1. And it is equilibrium, so it equals to 0. For the bottom picture, again, I have m2g. The distance is L1. And I have negative mg. The distance is L2. And equals to 0. So I'm going to solve one of the equations for L1 and the top equation. So L1 in the top equation is equal to, I could cancel g's from both sides if I set them equal to each other, and I'm going to have m1 over m L2, and then I'm going to plug it into L1 of the second equation. So I'm going to plug it in the second equation. So I'm going to have m2, and in this case, you see every single one of them has g. I can cancel these g's. So I have m2 times L1, which is m1 over m L2 minus m, and I cancel my g's. I have L2 is equal to 0. Do you see I can move my m L2 to the other side of the equation? So instead of saying equals to 0, I'm just going to move my m L2 to the other side and times both sides by m and divide both sides by L2. So I divide both sides by L2, and when I times them all by m, I have m1, m2 on this side, and on the other side I have m squared when I times both sides by m. So my m is equal to the square root of m1, m2. These are very common AP Physics multiple choice type of questions. This is a much easier question. So you have m1 is given 6 kilogram, m2 is 8 kilogram, and the stick is a negligible mass and has the length of 70 centimeters, and they want to know where should you attach a cord so the masses are balanced, or in other words, where is the center of mass. So if the full length is 70 centimeters or 0.7, then I'm gonna say, okay, this one is the center of mass, then this part is x, and this part is 0.7 minus x. And if this was the center of mass, which I do not know, I'm just saying, if that is the center of mass and I was balancing it here, then I would have m1g and I would have m2g. So if I want to find the center of mass, and this is probable question to have on AP exam, to find the center of mass for the system. So do you remember when we started center of mass and the torque, I said you can use sometimes one or the other to look for equilibrium. So to find equilibrium point, again, I'm going to say it is the sum of all the torques that is equal to 0, and I'm going to use exactly the same concept that we used in the previous questions. So I have positive m1g times the distance, which is x, and the other one is negative, so m2g, because it would make it rotate in the clockwise direction, and the distance is 0.7 minus x, and that is equal to 0. Every single one of these terms, so there's 1 term, 2 terms, 3 terms, I can divide all of them by g. And so what's left is, if I plug in the numbers, m1 is 6x minus m2 is 8, and then I have 0.7 minus x, and equals to 0. So if I solve this equation for x, I will get equals to 0.4 meters or 40 centimeters. So the distance, I'm going to erase it. So the distance from the beginning of the rod to where the level position should be is 40 centimeters. So you could maybe add some level support, and the masses should be balanced. Here's one interesting question that I found, and AP exam question could be possibly look like this, but more conceptual. I'm not sure if they're gonna make it more mathematical for AP Physics 1, but good question to do. So you see both blocks in the cylinder have kinetic energy, so we start with both of them having kinetic energy, but the cylinder has both rotational, or the sphere has rotational kinetic energy and the forward, right, the motion. So at first I'm going to do the block. So for the block, and I'm going to split it into 2, and then I'm going to do the cylinder. And because the cylinder is hollow, it's not solid, then it's the same as the disc. So it's inertia that I'm going to be using in this problem. Inertia of the hollow disc, or hoop, right? Inertia of the hoop is mr squared. And so if we start with the block has kinetic energy, and all this energy is going to go to the potential energy. So I have the kinetic energy of the block going into the potential energy of the block. So I have 1/2 mv squared is gonna go to mgh. The mass and the mass can be cancelled, and I have h is equal to 1/2 v squared over r over g, and that will give me 1.25 if I use g as 10 meters. So that's how high the block is going to rise. But the cylinder, the hollow cylinder, it will have rotational energy, and it will have even though the picture doesn't look hollow, it is hollow. So so it will have rotational kinetic energy and the forward energy. So I have kinetic energy rotational plus kinetic energy of the motion, and all of it is going to go to the potential energy. So the cylinder has more energy to start with because it rotates and it moves forward. So the height it reaches should be higher than the one for the block. And for the block, they said use the capital H for the height. So this is the capital H. So I'm going to plug in my equation. So the kinetic energy is rotational. It's 1/2. And then I have I, which is mr squared, and omega squared. And the kinetic energy of the motion is 1/2 mv squared, and equals to the potential energy, which is mg and lowercase h. It's a different height. And by now you probably remember the formula, the relationship between the linear velocity and rotational. So that's r omega. And I see r omega as well over here in my equation. So let's times all of them by 2 and then replace r omega. So if I times by 2, I only have m. And instead of r omega, I have v squared because both of them squared. The next one times by 2 gives me mv squared. And the last one times by 2 gives me mg and h. I see every single one of them has m. All terms have m. So I have 2v squared divided by 2g is equal to h. So h is equal to 25 divided by 10, which is 2.5 meters. So h is 2.5 meters. And then they ask you for the last part, the relationship between h over h. So that's 1.25. It's 2.5 divided by 1.25. So it's 2.5 divided by 1.25 and gives me 2. So the cylinder, the hollow cylinder, because it had more energy, it will reach twice the height of the disk, because disk only had the kinetic energy, the motion kinetic energy. I also wanted to look with you at this problem before we finish the video. So go ahead and read the question. See if you can set up the problem yourself, because I think this is pretty easy compared to what we have done in the past. So pause it, write down everything that's given, try to solve it, and let's look at it together. So here I wrote in green on the top right side everything that is given. I redrew the picture because I wanted more space for my writing. And the plank has the mass of 7 kilogram, and I have to place its mass, or the force of gravity acting on it, in the middle of the plank, which is L over 2. And then you have x1 and x2 is given. What I need to find is this distance right here, how far is, because the point of rotation is going to be the blue dot. So this is the point of rotation of my plank, and so I need to find that distance on the top. So if L is 4 meters, then this part right here is 2 meters, and x2 is 1.5 meter, then the one on the top is 0.5 meters. Then I'm gonna do the sum of all the torques equals to 0. So the sum of all the torques, because it's equilibrium, equals to 0 in this case, and the forces acting. So for the first one, F1, the force is 0, so I don't have to plug in into my equation, even though the distance is given. so I will ignore that one. So the only forces I'm looking at is mg. So m is gonna make it the mass of the plank, so that force is gonna make it rotate in the positive direction. So I'm gonna have mg, and the distance I just found is 0.5 from the point of rotation, and sine of 90 degrees, don't have to write that one because that's 1, and then minus mg, because where the cat is standing, the plank would rotate in the clockwise direction, which is negative, and the distance is x2, which is 1.5, and it is in equilibrium, so I'm gonna set it equals to 0, and I'm solving for the mass of the cat. All three terms, 1, 2, 3, can be divided by g, so g goes away, so the mass of the cat is equal to 0.5, the mass of the plank is 7, and divided by 1.5, and I get the mass of the cat is equal to 2.33 kilogram. So this concludes our torque problem solving for our lessons. If you have additional questions related to rotational motion, centripetal forces, or torque or center of mass, go ahead and email me and let me know which question you found that you didn't know how to solve, and I would be more than happy to make another video and explain how to solve that question. And thank you for watching this one, and follow the description links for more information or other videos to watch, and see you in the next video.